Welcome to a half-century journey from obscurity to triumph. What began as an overlooked hypothesis at the historic Karlsruhe Congress took 50 years to claim its rightful place. Join us as we trace how a once-ignored idea transformed into molecular reality, becoming a true cornerstone of modern chemistry. Welcome to the curious branding paradox of chemistry's most famous constant. In 1811, Amedeo Avogadro conceived the foundational hypothesis, yet never calculated its value. Decades later, Johann Loschmidt became the first to actually calculate the number in 1865, earning only a niche attribution. Ultimately, Jean Perrin proved the concept experimentally in 1909, named it Avogadro's constant, and claimed a Nobel Prize. Thus, Avogadro achieved scientific immortality for a number he never saw. To understand how this paradox unfolded, we must rewind to 1811. In 1811, Avogadro introduced an elegant hypothesis to reconcile gases and atoms. Equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. To explain why 2 volumes of hydrogen combined with 1 volume of oxygen produce 2 volumes of water vapor, he made a radical proposal. Elemental gases do not exist as solitary atoms, but as multiatomic constituent molecules. By allowing these paired molecules to split and recombine during reactions, the fundamental mechanics of chemistry suddenly made perfect sense. Despite his brilliance, Amedeo Avogadro worked in relative isolation in Turin, far removed from the dominant scientific hubs of Paris, Manchester, and Stockholm. A former ecclesiastical lawyer, he lacked influential students to champion his work and preferred quiet study over academic politics. He published his groundbreaking ideas in obscure local journals and never sought fame or engaged in public debate. Lacking a network or powerful advocates, Avogadro's profound vision remained sidelined on the periphery of European chemistry. In early 19th century chemistry, a fundamental clash of paradigms emerged between Avogadro's molecular theory and Berzelius's dominant electrochemical dualism. While Avogadro proposed that elemental gases could be polyatomic, held by a general attraction, and governed by universal volume rules, Berzelius insisted gases were strictly monatomic and bound only by opposing electrical charges, thereby restricting volume rules solely to elementary gases. To understand why Avogadro's ideas were rejected, consider the electrostatic repulsion barrier. Under Berzelius's dominant electrochemical dualism, chemical bonding required opposite electrical charges, like positive copper bonding with negative oxygen, to attract. Conversely, linking 2 identical atoms, such as 2 negative oxygen atoms, was considered physically impossible because like charges must repel. Bound by this rigid framework, the scientific establishment dismissed Avogadro's proposed diatomic oxygen as an absurd, ad hoc speculation. Without a unified system to distinguish atoms from molecules, chemistry descended into a half-century of confusion. In the 1810s, John Dalton rejected Gay-Lussac's volumetric data to preserve his theory of atomic indivisibility. By the 1830s, Jean-Baptiste Dumas recorded baffling vapor density anomalies, such as ammonium chloride displaying lower than expected molecular weights. By the 1840s, blurred definitions caused rampant errors in chemical formulas, frequently misrepresenting water as OH instead of H2O. Lacking consensus, early chemical science remained deeply chaotic. In 1858, a breakthrough arrived when Stanislao Cannizzaro published his Sunto di un corso di filosofia chimica, resurrecting Avogadro's neglected hypothesis. By systematically applying it, Cannizzaro established a single, unified system of atomic and molecular weights. He successfully resolved Dumas' earlier anomalies, proving they were caused by thermal dissociation, such as ammonium chloride breaking down at high temperatures to artificially double its gas volume. Through Cannizzaro's work, clarity finally began to replace decades of chemical confusion. At the 1860 Karlsruhe Congress, the distribution of Cannizzaro's Sunto created a powerful ripple effect across chemistry. Reading it transformed Lothar Meyer's understanding, making doubts vanish as scales seemed to fall from his eyes. For Dmitry Mendeleev, these newly unified atomic weights provided the vital key, leading directly to his landmark invention of the periodic table in 1869. Thus, a single distributed text catalyzed a revolution in our understanding of the elements. In 1865, chemistry moved from relative ratios to measurable reality. Austrian physicist Johann Joseph Loschmidt provided the first quantitative estimate of molecular populations. By applying the kinetic theory of gases and analyzing the mean free path of molecules, he calculated the actual number of particles in a given volume of an ideal gas. Through this breakthrough, Loschmidt successfully transformed Avogadro's 50-year-old qualitative rule into a hard mathematical reality. Between 1908 and 1909, Jean Perrin put Albert Einstein's 1905 statistical mechanics to the test, proving the invisible by tracking the visible. Using a specialized microscopic apparatus to observe colloidal suspensions of resin particles, Perrin carefully measured their random walk and sedimentation equilibrium. By tracking how invisible water molecules continuously bombarded these visible particles, he delivered the definitive experimental proof for the physical reality of molecules. By calculating Boltzmann's constant, Kb, and leveraging the universal gas constant, R, Jean Perrin derived the number of molecules in a single mole, approximately 6.7 times 10 to the 23rd per mole. He officially christened this landmark value Avogadro's constant in honor of Turin's visionary. Faced with such irrefutable quantitative evidence, even Wilhelm Ostwald, the era's fiercest anti-atomist, was forced to publicly concede to the physical reality of atoms, bringing a triumphant end to decades of scientific skepticism. In 1926, molecular reality achieved its ultimate vindication. Jean Perrin was awarded the Nobel Prize in Physics for his work demonstrating the discontinuous structure of matter. What began in 1811 as an unproven, dismissed hypothesis in an obscure Italian journal was officially codified as Avogadro's law. Over a century after its proposal, Avogadro's visionary concept became the undisputed foundation of physical chemistry, forever cementing its place in science. In 2019, Avogadro's constant completed its transformation from an experimental measurement into an absolute anchor of science. Under the historic revision of the SI units, the definition of the mole was permanently severed from the mass of 12 grams of carbon-12. Instead, Avogadro's constant was fixed as an exact, unvarying fundamental constant of the universe, 6.02214076 times 10 to the 23rd per mole. 2 centuries after its proposal, Avogadro's vision achieved ultimate mathematical perfection. Here stands the complete architecture of a scientific truth. What began in 1811 as a purely conceptual hypothesis was ignored for 50 years due to theoretical dogma. Through Cannizzaro's defense, Loschmidt's mathematics, and Perrin's experiments, it transformed into measurable proof. By 2019, it reached the absolute, fixed as an exact integer anchoring the SI system. Though the scientific method rarely guarantees immediate acceptance, it ensures that truth, no matter how deeply buried, will eventually dictate our understanding of the universe.